about this if you haven't heard of this. The idea generally is that if I want to sample an analog signal, I want to make sure that I'm not losing any of the part I'm interested in. And this guy named Nyquist, a while back, figured out that you needed to be sampling at least twice as fast as the bandwidth of interest. So in the cases like people mostly come out of engineering school, or the first time they look at this, they're always thinking of the low pass case, where that means if I have a signal that's 100 megahertz, then I must need to sample it at like 200 megahertz or 250 megahertz. Well, if I were trying to capture everything from 100 megahertz and down, that's true. But if I'm only trying to capture some stuff that's like centered at 100 megahertz, but maybe is a few megahertz wide, then I don't need to run that fast. So the trick is that at this sampling rate over 2, there's aliasing that occurs. So it's actually like chunks of the spectrum just fold back in from both sides. So you can figure out where that's going to happen. And the cool part is that, for example, our analog to digital converters have a very fast front end on them, which actually we can run them. We can put signals in that are up to 400 megahertz, even though we're only sampling in 64 megasamples, and we get reasonable results. So what this is good for in our case is it means that we don't need any, so for sort of regular radio guys, there's no analog mixer in the system. There's no like superhet anything. So basically no analog mixer, no analog oscillator, which basically gets rid of that whole problem, because otherwise you have to figure out how to make that coherent also. So the beauty of this from our point of view is we get the coherency, and all we have to control is the sample clock on the analog to digital converter. Okay, so we went and we said, all right, what's the simplest thing that could possibly work? And this was the two directional antennas, point one at the transmitter, one was about 120 degrees away. This was because it was towards the airport. 2 low noise amplifiers, and then one of these USRPs. Okay, looks like this was the setup. These are, you can kind of see there's 2 of these directional antennas. These were actually, we get them at Radio Shack in the US. They're for FM radio, and they're very inexpensive. They're like $25. By the time you get the mast and the stand and the cable, you probably got about $100 in each one. And then there's, you can see the other one in the other direction over there. The transmitter in question is on that mountain right there. There's a whole bunch of them over there, but that's where we're pointing the one at, and it's a clear line of sight. And then here is the sort of, in the field, so basically it's, laptop, it's duct tape, it's some cables, and the USRP is in the cardboard box under the table there. So we sit outside, we got this all set up, we're in the middle of the desert, and we say, okay, anybody see any airplanes yet? Okay, the first time out, we want to make sure that we have a prayer this thing's going to work. So we look and we say, okay, good, 737, westbound, and you log the time and say, start recording data, and the files are all time-stamped. And so we're basically collecting data from 2 channels and writing it to the disk. So we collect, an afternoon's worth of data. Then we go and we go, okay, so now let's run our untested analysis software, and let's plot up and see if we can see this range versus Doppler. So this is the idea, how the frequency shift of the thing and how far away it is. So we go, hey, all right, look at this graph. So the y-axis is Doppler. So this has lots of bins in it. So the way this was plotted up is there's like 256 possible frequency offsets that it could be at. And this is about 30 pixels wide here, 30 bins wide this way, which is about out to 30 kilometers. So I was looking, the airplanes were closer than 30 kilometers. I figured they ought to be in there. Well, I don't know about you, but I don't see any airplanes in there. So then we're going, okay, we got all this great idea, now what? So, we're big fans of let's just try it and see if it works. So then the question is, what's not working? Is it the hardware? Is it the software? On the GNU radio list, I'm notorious for saying, we need unit tests. Don't submit code without QA code. Well, okay, I'm going, okay, good idea. Maybe I should apply it onto my code too. So kind of we had some questions, like on the analog section, do we have the proper filtering? In fact, if you look, I don't know if I actually didn't show the block diagram, but in that simplest thing that could possibly work, we left out this piece called the bandpass filtering. It turns out for doing regular FM reception, it works, but part of the problem is that really, since everything is getting folded in here with no selectivity, you got all these potentially big signals on top of it. So it works okay for the big FM stations because they really still get bounced, but I think what's happening is that the small reflectance off the airplanes are getting swamped out. There's a question about antennas. Do we really have the right setup? Or the other question is the software working? So we go, aha, let's simulate first. So of course, the people I know who do this for a living, they said, you should simulate this. I'm like, okay. So now we get out our GNU Radio toolbox. We have an FM transmitter in there. We got all kinds of stuff, but we got narrowband FM or wideband FM. So we say, okay, I got a random audio signal. I'm putting it into my transmitter, and instead of putting it on the air, I just put it into the disk. And then I say, okay, now we want to simulate radar reflections. Okay, how do you do that? Okay, so you got the geometry. You got where's the transmitter, where's the receiver, how many targets do I have flying around? You know, you got some geometry. You basically, so you're simulating, the aircraft's flying this way at a particular altitude or whatever. And then you got to figure out the propagation delay that should be seen and the Doppler shift. So then we said, okay, let's try this analysis software on the reference signal, which was the simulated FM signal, and then basically you feed the analysis software the reference, which is basically the direct path, and then you send it the reflected stuff. So, hey, I see simulated airplanes. Okay. So this is actually great news, let me tell you. It meant that the first software didn't work. Now we think there's also probably some other things to fix yet. But so what we're looking at here is two fuzzy dots on a black background. But so the horizontal axis is the slant range. It's distance. So that's about 100 kilometers from the left to the right. And the y-axis basically has a 0 in the middle. Clearly, we need a little, tick marks on here. But anyway, zero velocity is in the middle. And kind of at the limits of plus and minus on there, it's about, maxes out at about 750 meters per second. So that's kind of the speed of a commercial airliner at cruise. So what we see are these two fuzzy things. Turns out there's lots of stuff you can do to tighten them up. There's, if you start thinking about how let me back up for just a second. So remember I was talking at the very beginning of the talk about how they had these radar systems where they sent out a pulse and then they stop transmitting and then they listen? Well, we don't control the transmitter, so it's on all the time. So the trick we get is that we can listen for a long time. And it turns out that the broadcast FM signal, particularly if it's turned to something like, very raucous rock and roll, has got really good properties for us. If they're just talking, it's not so good, seriously. But if they're really cranking it up, you have this idea that when how you figure out where, you're trying to make this time measurement, what you're actually doing is you're correlating, you're sliding kind of a delayed version of the signal against a non-delayed version of the signal, and it's brute force. You say, okay, try matching them up here, and you basically compute this. It's the correlation, but it's basically you take complex conjugate and sum them. And you can pick how big a window you like, and the bigger this window gets, the tighter you fit. So since I can do a second's worth of data, it's like 250,000 samples. These ones were done with 25,000 samples here. Anyway, so you get knobs to twist on, how does it look. Okay, so let me show you this thing animated. So again, the other thing to remember is that this isn't like X and Y position in this thing. This is like the raw return that we get out of the first cut of the analysis. So this is how far away, basically the distance in here is the difference in the direct path distance and the full reflected path distance. And then the Doppler, the Y component, is the rate of change with regard to time of that distance. So, hold on. So here are these two airplanes, and now we're going to see them actually moving around. And this is actually like 4 minutes worth of data. This would be like really 4 minutes worth of data that's running. We're sampling it every 5 seconds, and we're playing it back 10 times fast. So if you look at the one that started on the right, it kind of loops around and comes back. And the other one kind of came in and goes thing. So Let me do it again just so you see what happens here. So the thing to know is, I used 16 kilohertz wide Gaussian noise. Yeah. But I've also tried it with real FM signals I recorded off of the air, and that works too. We could throw FM. We could have like the selection of which is our favorite radio station, you know. So we could do that. The GNU radio transmitter, you just plug whatever data you want into it, and we can, you know, resample up or down to whatever rate you like. So anyway, the thing to note is that in reality, both of these simulated airplanes are flying a straight path. They're constant velocity, you know, headed one direction. But we see them, they appear to be bending. And again, the one to the left is coming very close to where we are, because basically see how the distance between the reflected path basically goes to 0 right there. It kind of flies right over us. And this one out here is flying horizontally but north of us. So now what we know is that we have a clue about extracting data. This is good. So then we said, aha, let's take the old data we collected the afternoon's worth and run it through this and see if we see anything. Well, it's not good. So we got other problems to fix. But we really do fundamentally think we're going to get there with this. We think this is a pretty good step. There's more to do, kind of the next piece of this. Meanwhile, so kind of where we go from here. So now we know we have software that we have a clue about. We should be able to use this simulated model to really go back and figure out how good does our analog hardware need to be, and what is it likely we should be able to see. I mean, as a friend of mine who I was talking to about this described, he said, you're gonna start with the airplanes that are casting shadows on your house, right? And I said, yes. So we have like, you know, I live in Reno, Nevada. The airport is relatively close. The airplanes fly pretty much over the top of the house. We should be able to see those things. They're big. It's not like we're trying to find little tiny things. My friends who are real RF experts, they keep telling me, you need helical filters. I'm like, okay. I'm looking for people who want to build helical filters. Those are actually a very cool mechanical engineering hack. They like to do them at 100 megahertz. They end up being about, they're like 10 centimeters by cylinder, 10 centimeters across and 5 centimeters tall. And there's like a little, so it's like a piece of copper pipe that then has like copper helix inside of it that's only got one end connected, the other end's freestanding, and it works because of the mechanics that are right inside of the thing. So those are very low loss, meaning that we don't, basically we select just the part we want and our signal isn't attenuated. So we might try some other things too, but that's, the people who are in the know keep telling me this is the answer, and I haven't found them. You can find them off the shelf at about 400 megahertz. They use them in lots of radios, but apparently they're not, I haven't found a supplier that just sells them to you. Other ideas on antennas. So we looked at, and again, this is from looking at some of the literature, what did other people make work? See, part of the problem may be that we're getting swamped out by the main path transmitter. You start thinking about this. This reflection off the airplane could be, you know, minimum 100 times smaller, you know, 20 dB down from the main path. So you think about it. You got like this spherical wave that's propagating out, and it hits something, and then it propagates back to you. So it's small. So one of the tricks that people have used is they need some way to keep the main transmitter from just really hammering them. So the guys at the University of Washington, they had this clever thing, you know, relatively unique to them, is they put the mountain range between the two, solved their problem. The other people put this big metal screen behind it, and it's a classic setup for, like in electromagnetic labs, there's like a canonical antenna they use for measuring field strength, and it's got that shape. So it's a big grid with two dipoles in front of it. The other thing are antennas called corner reflectors, and basically they're a quarter wave dipole. So again, that's a quarter wave of 3 is a nice smaller thing, and it's basically a big triangle, like this with a metal plate on the bottom. Those should work pretty good too. So that's the immediate short term. Then what gets interesting is, so we get the raw radar return, and we've got sort of, it's kind of like you think about you're doing your first order feature extraction. Then the other juicy part comes in here about, okay, well, it's nice to be able to determine where they're coming from. What is the angle of arrival? So then we start